Okay, so this is a project that I cooked up with Graham Pearson at the University of Alberta, and he's got a postdoc working with him, Kiwei Zhang, and a colleague, James Day, who's an expert on PGEs and magmas, and Graham, as you know, and Shui, they work basically on mantle xenoliths and things like that. And we thought we'd team up and address a problem that ore deposits people have, and that is whether or not um, you get any of the metals in magmatic nickel-copper-PGE deposits from um, basically the subcontinental lithospheric mantle. So SCLM, it's sometimes called, as I've got in the next slide, cratonic mantle. But the idea is this is what's holding up the continents. This is solid mantle, not convecting asthenospheric. So this is still convecting asthenospheric in this cartoon, this plume. It's a hotter part than the ambient mantle around it. And this is what's holding up all the cratons. And that formed back in the Archean, mostly when there were lots of komatiites and you had high degree partial melting of the mantle, and you left behind a lot of, well, basically just olivine. So it's a peridotite, almost a dunite. And not only that, but the olivine is Mg rich and therefore much less dense than the more phaletic, well, not phaletic, but anyway, more phalite component bearing mantle in around here. So this has held up the continents and explains why they haven't been broken up, because this is all very buoyant. So the idea, though, is that there are stages of time when these cratons have had subduction zones around them, and that parts of that have been refertilized. And these can be sampled in mantles, kimberlite xenoliths, and in basalt xenoliths. And so there are lots of different flavors, and that's the sort of thing that Graham works on. The model here is the one I was talking about. This shows sort of the craton margin model where the magma comes up. It gets steered over here. That's an original idea by Norm Sleep at Caltech back a long time ago, and it was taken up about 10 years ago by the Macquarie gang, Graham Bagg, and that also involved Griffin here, Bill Griffin, and that this would focus the melting. So this is decompressive melting here, and that you could then produce nickel deposits. And they're arguing that you get interaction with the subcontinental lithospheric mantle. Okay, this is debated. There have been sort of this gang here. Some of the names I noted was Bill Griffin. This is his wife, Suzanne Riley. This is one of their postdocs. And John Wonsky worked for Western Mining when I knew him. And then after I stopped seeing him so often, he worked for BHP. And then Nick Arndt well, you'll all know Nick Arndt from his work on komatiites. He sort of published a rebuttal of that. And then recently this has been resurrected by Dave Hallwell and Marco Fiorentini and colleagues as a way to sort of form some, well, less important deposits. It would be generous, I guess. So they've basically got a signature of that. I'm not going to talk about that very much. So I mentioned some of this in the other slide. It's highly depleted and buoyant, and whereas the Phanerozoic, actually, this is the Archean, is mildly depleted and a little less buoyant. And that's because when you made more modern rocks, you don't meld as much of them. You don't make komatiites anymore, or at least not very often. So as I mentioned, you can sample this in orogenic peridotite massifs, so these things that sort of billow up along the sides. I mean, you can abduct them in ophiolites and things like that too, but these are thought to be more representative of the mantle often, and a little less altered. And then inclusions. So as I mentioned, it was strongly depleted by the formation of komatiites. So that's Nick's main argument. He has a list of about 10 things he doesn't like about getting any metals from subcontinental lithospheric mantle, but the main one is that it's depleted. If you metasomatize it, it contains hydrophases that meld at lower temperatures. So fulgopite and amphibole, as it turns out, can accommodate significant amounts of nickel. Nothing else though, and that's critical. It's only nickel. Um, and so what'll happen is, of course, is you get low degree melting of that stuff is all you're going to get out of it. You just melt the hydrous stuff and you still leave behind the olivine. Um, and so you get quite irregular patterns, as we'll see. And then if you metasomatize asthenospheric mantle, which also happens, you can generate larger volumes of magma, and you can have mineralization that's systematically enriched in these elements, which we'll see as a characteristic, relative to all the platinum group elements. And Nicolas Tonnelier was the first one to point that out. He did his PhD here. And Yiguan Liu, who also did his PhD here, has focused in on the Chinese deposits in general. This was on Jinchuan here. Let me change that back to a laser. Okay, so looking at the ores, most major deposits have signatures that tell us they're from peridotitic asthenospheric mantle, not SCLM. Some deposits are enriched in these metals compared to the PGE. There's a few here, Pichinga, Voisey's Bay, Eagle, and most Chinese deposits, as we'll see. And then, as I mentioned, there's a couple of the ones that have really irregular patterns, and those are reasonable, but you probably even haven't heard of these. That's Ivrea zone is worldwide famous for being the deep pipes, ultramafic pipes in the deep crust. And Modor, which is in Australia, is an alkalic complex. May have a contribution from SCLM, but their patterns are quite different. And then we need to, if we're going to look at the ores, which we will, then we need to worry about fractional crystallization of MSS. We can avoid that by avoiding massive ores and alteration. So we can avoid that by looking at more mobile elements like cadmium and arsenic and antimony and so forth. And then metamorphic hydrothermal alteration is usually visible. All these things have different geochemical signatures. So I apologize. I had hoped to have these all plotted up in iogas, which has been all consuming for me lately. And but these are some old diagrams I put together for a paper with Dave Burrows, as I recall. And so these are some of the world's larger deposits. Apologies if you've seen this before, but just in case you haven't, have these sloping patterns when the elements are plotted in this order, more compatible down here, less compatible down here. And the komatiites hosted ones give a fairly regular pattern across here. There's a little bit of fiddling that could be done with this order because there's a lot of scatter that goes into these averages. But in general, things are, that's the order of compatibility, which is different from the way you'll see it in some published plots. Now, the same plots, though, and I've plotted Raglan for reference here, Pichinga, Voisey's Bay, and Jinchuan. And these are lots and lots of samples from Aldrich's compilation averaged. Well, I'll explain later. I mean, it's a lot of these elements that might be more diagnostic are missing. And then a lot of places, if you go and talk to the PGE people that work on mantle xenoliths, they don't analyze for nickel or copper or cobalt, which has been sort of the trouble we've had in compiling data for this project. Anyway, you can see all the PGE and just the PGE are all depleted, and they're all depleted about the same amount relative to, say, for example, Raglan. Now, these are going to move up and down with, the magma sulfide ratio, the R factor. But in fact, these are strikingly similar at this scale. So this is sort of spread out, and and quite different from nickel and, oh, sorry, copper and nickel and cobalt. So strongly depleted. So that's the pattern of what the major deposits are telling us, that we've got two types, and we've interpreted this as being from sort of quote normal asthenospheric mantle, and this being from metasomatized asthenospheric mantle. And that's because, you know, the Chinese deposits in particular, Jinchuan shown here, for example, are just surrounded by subduction zones. We really don't know why Pichinga has that metasomatized source, but the osmium isotopes tell us that's the case. Same with Voisey's Bay. Here's the Chinese deposits, and you can see the same sort of signatures. Some are more depleted in PGEs compared to copper and nickel. There's no cobalt information, unfortunately. And some are a little bit less in here, including Jinchuan. So these are even more depleted in PGEs. These are the komatiite-associated ones for reference. Here, a couple more other than the ones I've showed. So Thompson's in there, Perseverance in Western Australia. I think Mount Keith was already on there. Dumont in Quebec. And there's some that are enriched in PGEs. That's basically a PGE deposit. Okay, so this is the database that that James and Shui compiled, and I haven't actually added mine into this yet. And you can see on here, I hope you can see there's lots of these light blue lines. That's the data. So not every sample has all these elements, which is unfortunate. And I hope for more, but that's the way it turned out. So you can see, for example, these two samples have nickel and osmium and rhenium. So it was a rhenium osmium isotope study that just happened to report nickel. And then there's ones that are basically PGE studies. Here's palladium and platinum. They didn't do rhodium for some reason. Ruthenium, iridium, and osmium. So mostly a PGE study that included nickel, but not copper. So these are problematic, and I haven't decided on what the statistics are telling me. But I basically shown the 10th, the 50th, and the 90th percentile on here. So this is the high and the low. I didn't do the mean because I don't like averages. But anyway, highly variable rhenium osmium is one thing that's standing out here. A lot of crisscrossing over here. So that's telling us something funny is going on with rhenium osmium. But in general, the patterns here, like the ones we saw there, that they're basically sloping off in this sort of direction. And this is sort of what we'd expect by high degree mantle melting. And these are lower. These things, osmium, iridium, and cobalt would be, but none of these samples have cobalt. So that's why I need to add more data. But nickel and ruthenium, well, so basically nickel goes into olivine, and there's a bit of debate about what phase the ruthenium, iridium, and osmium are in. Some people argue it's an alloy that always goes with olivine. Some people argue it's in olivine, and there's papers that argue it both ways. Doesn't matter, they go together and it's pretty consistent. So those are being held behind in the olivine that doesn't melt, and these things are being preferentially incorporated into the melt phase. So that's what the pattern would look like and what the ore would look like multiplied by the partition coefficients if we had asthenospheric mantle. So the databases that James put together also had MORB, shown here in pink, and OIB, shown here in blue. And these are, again, the percentiles. MORB is depleted in PGE. That's been well known forever. Jim Crockett at McMaster published a lot on that back in the 70s and 80s. Because basically they're being retained in sulfide. The degree of partial melting to make MORB is low enough that sulfide is retained in the source, and all of the PGEs stay in there. And it builds up and builds up and builds up until it melts. And that was something pointed out by Tony Aldrich and Sarah Jane Barnes back in the 80s. Nickel's retained in olivine. The effect of the iridium and osmium is to sort of flatten this this pattern out down here instead of it keep sloping. But generally, again, that's a pretty good pattern. Copper's a little bit wonky, just missing so much data here for other samples. It'd be nice to know if all those were up there, but these are a little bit enriched in copper. So they may have contained a little bit of entrained copper-rich sulfides, and they're copper-rich because mafic magmas have higher copper to nickel ratios than not. So that's probably the explanation for that. So far, we haven't seen anything that, this is okay. The ores might look like this, but anyway, we'll get to the xenoliths in a bit. I plotted oceanic arcs up here because James had it in his database. They're flat in these elements, and that means that the sulfide was consumed in the source, and those are sort of flat. And again, the abundance is sort of going to depend on what else is melting and whether they're being diluted or not by melting other things that don't contain PGEs. And then they're variably depleted in these, and that means it was probably retained in olivine. These are, arc basalts are lower degree partial melts than commodioites or picrites and things like that. So they're probably being held behind in olivine. Continental arcs look like this, a little bit messier, but again, you got to be careful because, for example, there's a lot of missing data in here. You can see there's a huge range in osmium, lots of crisscrossing with rhenium osmium, which shouldn't really be the case. So I'm not quite sure how to work with that. I haven't had a chance to talk to Graham about that yet. So I think, maybe there's some alloys that might be holding back nickel and osmium. If the conditions are reducing, then you can get alloys, because that's a pretty good depletion there in nickel relative to ruthenium and so forth. So it could be like a nickel alloy or something like that. These are now abyssal peridotites. So these are, again, samples of the mantle itself, and they're pretty flat. That's been known for a long time. They're a little bit depleted in palladium, quite know how to reconcile that, and a little bit enriched, on average or up at the 90th percentile in gold. Gold's pretty mobile though, and so this could be alteration. Palladium's a little more mobile, quote hydrothermally, than the rest of these, but those are pretty flat, and so that's a pretty good idea of what subcontinental lithospheric mantle would look like. These are the cratonic xenoliths, and there's a couple different types up here. 3 types actually, and I guess I didn't label this, sorry about that. So there's ones that are, the dark orange here is the one that are actually, purely cratonic. The lighter orange ones here, or the golden ones, are the ones that are, craton peripheral. And then these green ones, I forgot, sorry, that's an old age thing. But they're all sensibly the same, which is plotted on the same plot. You can see that, again, if in some cases we've got some lines coming across here that are coming because there's missing data. But this is generally, pretty flat, but there's some distinctive characteristics here. And again, this has been known that these are, on balance, depleted in palladium, copper, and platinum, and undepleted in all these other things. So we're fractionating the PPGEs, the platinum group PGEs, from the iridium group PGEs, and that would include, in this case, rhodium. Rhodium sometimes switches back and forth whether it behaves with iridium or whether it behaves with platinum. So if we then take these, the magma that would have been in equilibrium with this, and then, upgrade it with partition coefficients, which would be, broadly similar for palladium and platinum, for example, we should get a pattern for an ore that looks like this. It would be depleted in platinum, copper, and palladium. And of course, that's not what we see. Most of the ores have a slope like that. Now, these are interesting, and I need to break these down because they've been lumped in Graham's database. So this is Shuai's and Graham's database here. So that's their work, and their work in compiling it. And these are so-called mica amphibole rutile ilmenite diopside, which is a mouthful, so they're called marid xenoliths. And these are PIC, phlogopide ilmenite CPX xenoliths. And these are the ones that are clearly metasomatized the most. They're, you know, they've been juiced. And again, frustratingly large amounts of missing data in here. For example, right here, all those lines shooting across, basically missing data, no iridium and osmium data, just nickel. There are lots of nickel data in these database, cobalt, iron, zinc. Interestingly, they're better at copper. So, but less in the way of PGEs than I would like. So anytime you see a little kink here, then there's a data point there, but otherwise we're missing some data. So I have to go out and do some searching on my own to get more data in here and dig it out. Basically, PhD theses are the best place to find it because it hasn't been published. The point remains, though, that in those cases, there's a couple groups here. There's a group that's enriched in copper and one that's depleted in copper. I don't know if that represents those or not. I just ran out of time and didn't quite sort that all out before showing you where we were. And but there's a lot of them that are depleted in copper relative to platinum and palladium and certainly to gold and leads over here. There's a bunch of other elements that would normally fit in here. I don't know if I showed you the full diagram, but there's all the so-called tabs. So the tellurium, arsenic, bismuth, antimony, and tin all fit in here and partition into sulfides and are less compatible than all these things over here. And so ideally, we're going to end up with more extended patterns. Okay, interim conclusions. So not differed much from what I had to say last time. We think most of them are from asthenospheric mantle and less commonly from metasomatized asthenospheric mantle. What I want to do is back model all these. So I want to calculate the melt that's in equilibrium with those, and MELTS can do that. The MELTS computer program by Mark Yorso. And then apply some sulfide partition coefficients to that, and then model the type of patterns we would expect. So that's something we do all the time. And we just need to do it to this stuff. Obviously there's some that maybe came from a metasomatized subcontinental lithospheric mantle, Modor and Avray. I didn't show you those, but they're wonky patterns. And so, I think the prospectivity is based more on high magma flux and access to crustal sulf than mantle composition. That's because we've got a couple different mantle compositions here, and we've even got a third type here of highly metasomatized. And the only difference is that these make world-class deposits and these don't. So completed are the databases by Shuai and James, and I've got all the calcophile elements in nickel copper PGE deposits that I've just added in this morning, but I haven't plotted. And then I've written an IOGAS script that helps me plot these up. I've done an outline of the paper, so this is basically what I had done last time, except we've now got all these databases finished. I need to break down more by locality. That's all in the database, but IOGAS, you've got to tweak some things to get it to plot different symbols for different localities, that sort of thing. I need to find more data. That's unfortunate and a bit sad, but I need more data for more elements so that I'm not looking at just rhenium and osmium. So after that, I need to finalize the plots and do the models. That's pretty quick. So it shouldn't take too long. So that's where we are on that. Again, I don't know if there are any questions, just a status report.